welcome to another module in this massive open online course. So, in this module let us start looking at frequency division multiplexing. Okay. So, in this module we will start looking at a different concept, that is frequency division okay, frequency division multiplexing. Now, the key word here is multiplexing. Okay. Notice that we have this term which is called multiplexing. What is the meaning of this term multiplexing? Now, notice that multiplexing basically means that several signals, multiplexing means multiple signals are combined into a single composite signal for transmission over the channel. Alright, thereby you are using the same channel for the transmission of not a single signal but multiple signals. Okay. So, the key idea behind multiplexing is that multiple signals correct, multiple signals are combined signals are combined into a single composite for transmission over the channel. For transmission over the channel. Okay. So, multiple signals are combined into a single. What is the advantage of this? The advantage of this is you are using the same channel, right, the same channel for the transmission of multiple signals instead of a single signal. Okay. So, this makes the channel usage efficient. So, same channel is used for the transmission of multiple signals. So, basically the channel usage becomes very efficient. Okay. And now, multiplexing is done in the frequency domain. So, there are various ways to do multiplexing. So, when multiplexing is done in the frequency domain, that becomes frequency division multiplexing. That becomes frequency division multiplexing. Okay. So, frequency division multiplexing is FDM. Alright. When a large number of signals, correct, large number of signals, right, are multiplexed in the frequency domain, that is they are separated by different frequencies, that becomes frequency division multiplexing. So, you take a large number of signals, multiplex in the frequency domain, make a composite signal, transmit over the channel, correct. For instance, when you look at a typical radio receiver, correct, we have a large number of radio stations, all of them are transmitting over the same channel, alright, and we are able to tune the receiver to the appropriate radio station and receive the signal corresponding to that appropriate radio station. This is an example of frequency division multiplexing, where a large number of signals are multiplexed, right, multiplexed into a single composite signal and transmitted over the same channel. Now, how is this done, frequency division multiplexing? This is done by translating the different signals through different carrier frequencies. For instance, let us take a look at this. how is this frequency division multiplexing done? All right. The several signals are translated to be multiplexed, okay, that is the key here, to be multiplexed are translated different carrier frequencies, center frequencies, or to different they are translated to different carrier frequencies. For instance, if you take a look at this, let us consider a simple example. Let us say I have these 3 different signals, correct, with spectrum M1F, let us say this has spectrum, this is the spectrum of signal this is M1F, take another signal M2T, this is the spectrum, this is the spectrum M2F, take another signal M3T, okay. This has spectrum M3F. Now, what I am going to do is I am going to take this signal, I am going to take this signal, I am going to translate it to carrier frequency, I am going to translate this to carrier frequency F C1, okay. Now, I am going to take this signal, I am going to translate this to a different carrier frequency, let us say I translate this to FC2, I am going to take this signal, I am going to translate this to a different carrier frequency, let us say FC3, okay. Now, I am going to combine all these things and transmit them over a common channel. Okay. So, what I have done is I have taken the first signal with spectrum M1F, correct, first signal with spectrum M1F, I have translated this to the carrier frequency FC1. I have taken the second signal, right, spectrum M2F, translated it to a different carrier frequency FC2. Third signal, translated it to a different carrier frequency FC3. So on and so forth, right. I can keep adding number of signals as long as I am translating them to the different carrier frequencies, finally combine them to form a composite signal and then transmit them over the common channel. Okay. So, the spectrum of the combined signal will now look as follows: the composite signal spectrum. If you look at the spectrum of the composite signal, the spectrum of the composite signal will look as follows. I will have in the frequency domain, this is F, I will have the spectrum 1 that is translated to, I will have spectrum 1 that is translated to FC1. Okay. This is your spectrum 1 which is translated to FC1, correct. Spectrum 2 that is translated to FC2, and spectrum 3 that is translated to FC3. So, this is what M1 F minus FC1, this is corresponds to M2 F minus FC2, and this corresponds to M3 translated to FC3 F minus FC3. Okay. So, this is your spectrum of the composite signal. Okay. And therefore, as I have already told you, this is the spectrum of the composite signal. Now, this composite signal is transmitted over the common channel. So, basically what are we doing? We are multiplexing M1T, M2T and M3T for transmission over the composite channel. They are multiplexed in the frequency domain, therefore, this is frequency division multiplexing. So, M1T, M2T, M3T are multiplexed in frequency domain for transmission over channel. Okay. And this is basically, this is nothing but this multiplexing in the frequency domain, this is nothing but your frequency division multiplexing. This is nothing but frequency division multiplexing or FDM. Okay, this is frequency division multiplexing or FDM. Now, at the receiver we have to separate. So, these signals are multiplexed, we have a composite signal. Now, at the receiver we have to separate these signals to extract the individual signals. Alright. Now, obviously, since these are separated in the frequency domain, we can extract each signal by appropriately band pass filtering at the corresponding center frequency. For instance, to extract M1, I have to filter at FC1. If I have to extract M2, I have to consider band pass filter centered at FC2. To extract M3, I have to consider band pass filter centered at FC3. So, therefore, at the receiver, the multiplex signals are separated by band pass filters. So, this is at the receiver, the multiplex signals are separated by, these are separated by band pass filters, correct. So, what are we doing? We take the received signal, we band pass filter, we pass it to an appropriate band pass filter, correct, BPF with center frequency, for instance FC1, another BPF with center frequency FC2, another BPF with center frequency naturally BPF with center frequency FC3. Now, this is the corresponding carrier frequency for the first band pass filter is FC1. So, this I demodulate with FC1, corresponding carrier frequency is FC2, therefore, demodulate at FC2, corresponding carrier frequency is FC3, so therefore, demodulate at FC3 and then pass it through the low pass filter. Pass it through a low pass filter. Okay. So, you get M1T, M2T, M3T. Okay. So, you are demodulating with FC1. So, this is band pass filter centered at FC1. Okay. For instance, this represents band pass filter centered at BPF centered at FC1. Okay. Then demodulate by FC1 or demodulate by carrier frequency FC1. Okay. Next we have band pass filter centered at FC2, demodulate with carrier frequency FC2, band pass filter centered at FC, demodulate carrier frequency FC3. Okay. And then we are able to separate. Okay. So, this will give us your M1T, give you your M2T, this will give M2. Now, this is basically your demultiplexing. Demultiplexing to extract M12T, M2T and M3T. Okay, demultiplexing nothing but you have a composite signal, from that you are extracting the separate components M1T, M2T, M3T. Now, let us look at the condition for this frequency division multiplexing. Now, if you look at the condition for frequency division multiplexing, you will notice that, for instance, you have here carrier frequency FC1, okay, and you have here carrier frequency FC2. Now, the spacing between them is FC2 minus FC1. Now, let us say this signal has bandwidth W1, this signal has bandwidth W2. Now, W1 plus W2 should be less than FC2 minus FC1. You observe that the sum of the bandwidths should be less than FC2 minus FC1 to avoid spectral overlap, right. Otherwise, the translated spectra are going to overlap. So, we must have, to avoid overlap, what we see is the condition in FDM to avoid overlap, we must have FC2 minus FC1 greater than or equal to W1 plus W2. Okay. This means that basically your carrier frequency separation must be greater than or equal to the sum, carrier frequency separation must be greater than or equal to the sum of bandwidths. Now, this is for DSB. Okay. However, for SSB, now if you look at SSB modulation, again let us consider the 3 spectra. We are transmitting only a single sideband. Now, if you look at SSB, you will notice something interesting. At SSB, again if we have FC1, we are transmitting only a single sideband. Let us say we are transmitting upper sideband. So, this is basically your W1. Now, this is FC2. Again here you are transmitting only upper sideband. So, this is W2. Now, this is FC3. Here again you are transmitting only the upper sideband W3. Now, if you can look at this, this is the spacing FC2 minus FC1. This is the spacing FC2 minus FC1. We see that FC2 minus FC1 need to be only greater than W1. So, for no overlap, so this is with FDM with SSB, frequency division multiplexing plus SSB. Now in single sideband modulation, right, SSB stands for, I hope everyone remembers, SSB stands for single sideband modulation. In particular here we are using USB, transmitting only the upper side bands, right. In particular here we are transmitting only the upper side band. So for no overlap, we need, this implies FC2 minus FC1 greater than or equal to W1. Similarly, FC3 minus FC2 greater than or equal to W2 and so on. So basically the point is, the difference between the carrier frequencies, alright. So the point here is that the difference between the carrier frequencies has to be only greater than the bandwidth, not the sum of the bandwidth. Therefore, you can space the carriers more closely, which means you are saving the total bandwidth. Okay. So SSB is more efficient in that way, in frequency division multiplexing. The total bandwidth required is much smaller. Okay. So here spacing needs to be only greater than or equal to bandwidth. Therefore, total bandwidth required total bandwidth required for FDM plus SSB, that is frequency division multiplexing with simple sideband modulation, is much smaller than the bandwidth required for FDM plus DSP. In fact, FDM plus SSB will, you can see that it requires half the bandwidth of total bandwidth of FDM with DSP, alright, similar to the advantage of SSB over DSP. Therefore, FDM plus SSB is much more efficient in comparison to FDM frequency division multiplexing with DSB, double sideband. So FDM plus FSB. So which implies FDM plus SSB is very efficient. FDM plus SSB is very efficient. Let us take a simple example of AM broadcast again. Or AM radio broadcast. AM is amplitude modulation, AM radio broadcast. In AM radio broadcast, we have carriers in the 540 kilohertz to 16 kilohertz band. Okay. Now carrier spacing is 10 kilohertz, the carriers are spaced 10 kilohertz apart. So carriers are spaced 10 kilohertz apart. So if you look at carriers, these are spaced. So you start at 540 550 kilohertz, then you have the next carrier at 560 kilohertz, so on and so forth. You will have carrier, the last carrier will be at, obviously this is not according to scale, the last carrier will be at 1600 kilohertz. So carrier spacing, if you can look at this, carrier spacing is only 10 kilohertz, that is your FC2 minus FC1. Okay, carrier spacing is only 10 kilohertz. However, the message bandwidth W is typically around 15 kilohertz, alright. So, W is approximately equal to which is basically greater than your carrier spacing, which means that two carriers which are adjacent to each other, that is 10 kilohertz separation only, cannot be used for transmission frequency division multiplexing, alright, in the same area, because if there is, let us say frequency 540 kilohertz being used, another signal 550 kilohertz at carrier frequency 550 kilohertz, then there is going to be spectral overlap between these two signals and they are going to interfere with each other. Therefore, since the message signal bandwidth in AM radio is typically around 15 kilohertz, the adjacent carriers cannot be used for transmission in the same geographic area. So, adjacent carriers have to be deployed in widely separated geographical areas, so that there is no interference. So, the adjacent, so the carriers that are employed in a certain geographical area have to be widely separated, alright. Adjacent subcarriers cannot be employed in the same geographic area, alright. Otherwise, they are going to, these signals are going to interfere with each other. So, adjacent carriers, so carriers, so in AM radio, adjacent carriers in AM radio, adjacent carriers are not used at the same location. Okay. In AM radio broadcast, adjacent carriers are not used adjacent subcarriers are not used in same geographic location. These have to be widely separated. So, adjacent subcarriers have to be used in widely separated locations, so that there is no interference. So, widely separated. These have to be used in widely separated locations, so that there is no interference. Okay. So, that is basically the point. Okay. So, what we have is in AM radio broadcast, we have carriers from 540 kilohertz to 1600 kilohertz at a spacing of 10 kilohertz intervals, alright, but the AM message bandwidth is 15 kilohertz, which is greater than the carrier spacing. So, adjacent carriers cannot be used in the same geographic location. Alright. So, in this module what we have seen is frequency division multiplexing, the methodology of frequency division multiplexing, alright. What is the motivation for frequency division multiplexing? To combine, to multiplex several signals, right, to multiplex several signals into a same composite signal for transmission over the channel, alright. And if it is done in the frequency domain, this is frequency division multiplexing, which is achieved by transmission to the different carrier frequencies, alright, such that there is no spectral overlap, and at the receiver, alright, they are separated with different band pass filters and modulated, demodulated using the different carrier frequency, alright. And also we have seen an example corresponding to AM radio broadcast, alright. So, we will stop here and look at other aspects in the subsequent modules. Thank you.